All right, so this is number 6. They give us f of 0 equals 0, derivative at 0 is 1, the first derivative. And then if you want to find a different derivative at 0, you can pick a number to plug in for n and then evaluate that. So if n is bigger than or equal to 1, you can use this formula to get those derivatives. It says a function f has all the derivatives for orders from -1, x -1 to +1 that satisfy the conditions above. The Maclaurin series for f converges to f of x for absolute value of x less than 1. So they're giving us that interval of convergence, right? So letter A, and this is kind of nice how they did this here, because a lot of times they'll just say write out the first 4 non-zero terms. It says show that the first 4 non-zero terms of the Maclaurin series are, and then it gives them to you. So it actually like tells you the answer. You just need to figure out how to get there. And then it wants you to write the general term. So it's actually kind of nice because they actually tell you the answer. You just need to like justify it. Now I always write these out, just staying organized, like I have to do this. Right, so it's the nothing derivative over 0 factorial x to the nothing, and then the first derivative over 1 factorial x to the first, and then the second derivative over 2 factorial x to the second, and so on and so forth. I just like to write it out because it keeps me organized. Now they said the first 4 terms, but this one's going to be 0. F of 0 is 0. So they said the first 4 non-zero terms, so I'm actually going to have to go one further here. All right, and then we're going to evaluate these. So f prime of 0, they said that that's 1, and then this is over 1 factorial, and then x to the first plus. All right, now the second derivative, here's where we have to use this formula to evaluate that. If we want the second derivative, we're going to plug in 1 for n, because 1 plus 1 would give us 2 here. So we're going to plug in 1 for n and evaluate this. So that would be -1. And then the first derivative at 0, which they said was 1, because this is saying like, hey, go back to the previous one. Right? That's 1, they told us, over 2 factorial x squared. All right, third derivative. If we want the third derivative, we're going to plug in 2 for n. So this is going to be -2. And then it says go back and get the second derivative, which was this right here, which was -1. So it's like go back and get the previous one. Over 3 factorial x to the third. All right, and then fourth derivative, we're going to plug in 3 for n. 3 plus 1 would give you 4 here. So that's going to be -3. And then go back and get the third derivative, which is this one. -2 times -1 would be 2. And then over 4 factorial x to the fourth. So it's awkward because it's like, hey, go back and get the previous one. So like this one was -1, that's what went right here. And then -2 times -1 is +2, that's what went right here. So simplifying this down, this would just be x. This is 1x to the 1, and then this would be -1/2 x squared. 2 factorial is just 2 times 1, so that'd be 2. Plus, because these negatives cancel, 3 factorial would be 6. So 2/6 is 1/3 x cubed. And then -6 over 24. 4 factorial would be 24. So 6/24 is 1/4. But at that point, they gave you this. They just said, show that. So we're doing like the work to show where this came from, but they gave you this answer. And then we have to write the general term, right? So this is alternating, positive, negative, positive, negative. So we're going to need a -1 to the n plus 1. And then the denominator is just n. This would be over 1, over 2, over 3, over 4. So first term, second term, third term, fourth term, that's just n. And then x to the n. And then I like to put that we started at 1, like this is the first term, second term, third term, because sometimes n can start at 0. This would be like considered the 0th term. So this is your general term starting at 1. All right, letter B. Determine whether the Maclaurin series described in part A converges absolutely, converges conditionally, or diverges at x equals 1. Explain your reasoning. All right, so we're going to use this general term right here, which is really unfortunate because if you didn't get this general form, then you'd be stuck for the rest of this. But This wasn't too difficult of one to write. We're going to plug in 1 for n. So this would be sum from 1 to infinity. And we're going to plug in, or I'm sorry, we're plugging in 1 for x. I think I said n. I'm sorry. We're plugging in 1 for x. It said when x is 1. So 1 to any power is just going to be 1. You can kind of ignore that. It's just going to be -1 to the n plus 1 over n. So we're going to see if that converges or diverges. That's an alternating series. So I'm going to do the alternating series test. The limit as n goes to infinity of 1 over n, that's going to go to 0. That's the first thing we have to show. And if you plug in n plus 1, that has to be smaller than just the terms have to be decreasing. And that's true as well. This is going to be smaller. So this converges by the alternating series test. Now they said, does it converge conditionally or absolutely? So we found that that converges. Now we need to do the absolute value of that. And so if you absolute value that, it's not going to be alternating anymore. This would just be 1 over n. And so that's a p series where p is 1, and so that's going to diverge. P has to be bigger than 1. So diverges because p is 1. So this one converges, but the absolute value diverges, so it converges conditionally. If this had also converged, it would converge absolutely. And if they had both diverged, then obviously it would diverge. All right, letter C says, write the first 4 non-zero terms and the general term of the Maclaurin series 4. Let me write this out. G of x equals integral from 0 to x, f of t dt. All right, so we're looking back at this, what we have right here, and we're just going to do the antiderivative of it. So you're just going to do the antiderivative of these terms. And again, they gave you this. In part A, we were just like showing where it came from. It was nice. They actually gave you these terms. So we're going to do the antiderivative for that. So for x, that would be 1/2 x squared minus, and then you'll have a half, and the antiderivative for this would be 1/3 x cubed plus, and then for this term, you have that 1/3 there, and antiderivative for x cubed would be 1/4 x to the 4th, and then minus 1/4 times 1/5 x to the 5th. And then I'm not going to have enough room to put the general term in there. So again, it's alternating, positive, negative, positive, negative. I have to come down to the next line because I ran out of space. So -1 to the x to the n plus 1 because it's alternating. And then in the denominator here, this one would be 1 times 2. This one is 2 times 3. And then this one's 3 times 4. And this one's 4 times 5. So it's n times n plus 1. And then x to the, was it n or n plus 1? Because if this is our first term, we're starting with squared, so n plus 1. And then this is for n bigger than 1. Again, I just like to write where it starts because, again, sometimes, like I'm calling this the first term and this the second term and this the third term, but sometimes they start with the 0th term. So it's always good to just say, where you started. All right, and then part D, it says, let p sub n of a half represent the nth degree Taylor polynomial for g around 0 evaluated at a half, where g is this function. So g is what we wrote out right here. Use the alternating series error bound to show that p sub 4 of a half minus g of a half is less than 1/500th. Okay, so your alternating series error bound states that this is going to be less than the next term. So for this one, we're using the 4th degree polynomial. It's going to be smaller than the 5th term, or the term, not the 5th term, the term that has the 5th power. If this is the 4th power polynomial, we're going to look at the term that has the 5th power. So this is the term that we're going to be looking at. All right, so that's going to be less than absolute value of this term, and x is a half. We want to evaluate it at a half. So this would be negative a 4th times a 5th would be 1/20th, and then 1/2 to the fifth. And so when we absolute value that, it'll be positive. It'll be 1/20th times 2 to the fifth is 32. So 1/32. 32 times 2 would be 64. If I just double 32, that's 64. And then the extra 0 there, 1/640th. And they just wanted us to show that that's less than 1/500th, which is true. 1/640th is less than 1/500th. And so that's all you needed to do there. So again, whatever one it says, you just take the next term. It's the n plus 1th term. So if this is the 4th power, you're going to use the term that has the 5th. All right, so let me go back and show you what the points are for this one. So for part A, it is a point for getting these derivatives. So those together are a point. So basically for using this formula to get those derivatives. And then it was a point for verifying it. So showing that it comes out to what they told you it was going to come out to. And then a point for writing the general term. All right, part B, it just said 2 points for the whole thing. Again, I like to believe they would split that into 2 though, 1 for each of these that you had to check whether it converges or diverges. So how many points am I at so far? 1, 2, 3, 4, 5. I'm just going to make sure I'm going to add this up to 9. All right, and then for part C, it was 1 point for the first 2 terms and then 1 point for the second 2 terms. So basically 2 points for that. I feel like that was one of the easiest parts of the whole question. You're just doing the antiderivative of that. And then 1 point for the general term. And then this was only worth 1 point because you just had to get the term that had the 5th power and then plug in a half and just show that it was less than 1/500. So that was only worth 1.